So we'll have 7 states, which is down, init, two-way, xstart, exchange, loading, and full. Each router will transit all these 7 states till it reached full. When a router will reach full state, this will mean that the OSPF adjacency is formed. So the first state is down, and in this state nothing happens, and the routers are waiting for a start event. Each router will then send a hello message to the all routers multicast address, and the minute they will send this hello message, they will transit into the init state. A router will transit in a two-way when the hello packet will be received by the router with the neighbor router ID listed in the neighbor section. And at this point, designated router and backup designated router will be elected. Routers will send a database description packet and decide who is the master. And as soon as the routers send the database description packet, they will transition into the xstart state. So they are sending the database description with sequence number of x. R1 is stating that he's the master, and R2 also think he's the master. After that, after the election is completed, R1 will become the slave, and it will send the database description with the sequence number, and R2 will be the master, and it will send the database description with the sequence number. Okay, so now routers will transit into exchange state, and they will start exchanging database description packets. And if a router will receive an LSA header which didn't know about it, it will send an link state request packet. So let's say, for example, that R2 is having its database full, and it doesn't have any missing information. R1 doesn't have its database full, so it will send link state request messages. R2 will send the ls update messages, and it can be several ls update messages and ls request messages. And after all the messages will be received by R1 and its database will be completed, it will also transition into the full state. So when you see that two neighbors are in the full state, that means that they are fully synchronized. And also forgot to mention here, when the R1 will receive the ls update, it will also send an ls acknowledge that will inform the R2 router that message has been received and the database has been updated with the new information. We can have several methods of implementing OSPF, and one of these methods is the OSPF implementation on a broadcast media, aka we'll have a switch in the middle. So you can see that we have the router IDs configured on each router, and the router ID most of the time will be the loopback address of the router. If it is not specifically configured as a router ID in the router configuration, but almost in all cases we are using router ID configured as the loopback address, and each of the routers have their priority, which is by default 128. So each router will send and receive the hello packets, which are being sent to 224.0.0.5, which means that this is all OSPF routers, and the packet will be like that. Packets that are sent from hello packet that is sent from R1 will have the router ID of 1111. It will announce its priority. It will announce the designated router IP, which is all zeros because we don't know who is that, and the backup designated router IP, which is also all zeros. The rest of the routers will do just the same, will announce the router ID and the priority. Next phase is that designated router and backup designated router will be elected, and R3 will be the designated router and R2 will be the backup designated router. And hello packets will look like this. You can see that the designated router was elected because it had a higher router ID, and R2 was elected as a backup designated router because his router ID was lower than R3's. But let's say that if we had a higher priority here, it would override the router ID, and let's say that RT would have 129. No, let's say that R1 will have 129. It would be the designated router instead of Drudder. How the hello packets will look now? We'll have it will look the same, but every hello packet from now on will include the designated router IP and the backup designated router IP. Okay, so as soon as R1 will have OSPF enabled, it will start sending hello packets to OSPF router broadcast address, and it will have the DR and BDR IP of all zeros, meaning that it is asking for a designated router and backup designated router. And the hello messages will be sent for 46 seconds, which is the wait timer. And if no response, it will assume that he is the designated router. Okay, so when the R2 will come up, it will send its hello packets. Again, it will have the router ID of 2222, priority of 128, and the designated router IP of all zeros, and the backup designated router IP also of all zeros. And it will learn that R1 is the designated router, and if no response from other backup designated router will be received, for 40 seconds, it will assume that he is the backup designated router. So now R3 will come up and it will send his OSPF packet. So R3 will try to discover the designated router and the backup designated router by sending hello packets with all zeros. It will receive hello packets from R1 and R2, and it will update its hello packet according and thus becoming the Drudder. Why did I show you this scenario here and after that this scenario here? I wanted to say that if a router becomes the designated router, it will stay as a designated router. If a router with higher priority or router ID will come up, it will not take the mastership. The mastership will remain always on the router which was started up first, unless it will fail. Okay, so let's say that we have two more routers, and now we are using two OSPF multicast addresses, like 224.0.0.5, which is all OSPF routers, and 224.0.0.6, which is the designated router and backup designated router only. Let's say that the designated router will send a routing update or a link state update. It will use 224.0.0.5, which is the all OSPF routers address. When the Drudder will send a routing update or link state update, it will use 224.0.0.5. Okay, now R3 will send the link state acknowledgement packet using the 224.0.0.6 address, because designated router and the backup designated router need to get the acknowledge. Now R2 will send the link state acknowledgement packet also using the 224.0.0.5 address, thus informing the other routers that it is still alive. Let's say that if the BDR will not send the link state acknowledgement packet, other routers will assume that that it is down and will try to take the packet designated router role. Now let's see what is happening when a router will send a routing update or a link state update. It will send its LSU to 224.0.0.6 and only BDR and DR will receive this message. The designated router will send the LSU to 224.0.0.5 so all the routers can receive it. So again, when a router will have an update, it will use 224.0.0.6 address to send the OSPF updates to designated router and backup designated router. The designated router will receive this update and it will use all OSPF routers multicast address and will send this update to all of the routers. The acknowledge process is the same. The backup designated router will send the acknowledge to all OSPF routers and the others will send the acknowledge to DR and BDR only. Let's say that the backup designated router will have a link state update to send. It will send it to 224.0.0.5, which is the all OSPF routers. The designated router will send the link state acknowledgement to all OSPF routers address, and thus it will inform others that it is still alive, and the others will also send the acknowledge to DR and BDR only. Why do we need this mechanism? Why can't just all the routers send their updates using the 224.0.0.5, which is all SPF routers? Okay, so imagine that this router here will send an link state update. It will be sent to all of the devices, and after that all of the devices will send another LSU, and after each device receives the LSU, it will have to send an LS acknowledgement, and very soon this whole network will be full with OSPF update messages. And you can see that we have only 5 routers here, but imagine in a network which have 20 or 30 or 100 routers. It will be a disaster, and the bandwidth will be consumed just for the update and acknowledge messages. Okay, so moving on. In OSPF, routers will have different neighborship states. If the neighborship states between a router and another router will be two-way. They will know that each of them exists, but they will not go full state as they are not sharing routing updates. So R3 sees R4. So R3 will be in a two-way state with R4. R5 and R4 will be also in the two-way state, and R3 and R5 will also be in the two-way state. Also DR and BDR. These two should be always in the full state because they should have the databases fully synchronized. A designated router and a router will also be in the full state because their databases should be also fully synchronized, and the designated backup designated router and routers also are in the full state. So only router to router relationship is in a two-way. Also, we can have another type of OSPF implementation, and this is the most popular one, let's say. I mean, I've never seen this type of implementation of OSPF in real life, but it is a good exercise, and you might not know when you need it. So moving to our triangle here, we have 3 routers. R1 and R2 have a point-to-point interface, and you specifically configure this to be a point-to-point interface. And we also have regular links between R1 and R3 and R3 and R2. In this case, the BDR and the backup designated router and the designated router will be elected on each segment. So let's say that on this segment we'll have R1 as the DR and R3 as the BDR, and on this segment we'll have R3 as the DR and R2 as the BDR. But in fact, if I'm looking here on the segment R3 and R2, R3 will be the designated router, as its router ID is higher than R2's router ID, and R3 will be the DR and R2 will be the BDR, and R3 will also be the DR for this segment here. But let's say if on R1 we have the higher priority, then R1 would be the DR and the R3 will be the BDR in this segment here. Also, we have an interesting case here. If we configure the point-to-point link on each side, meaning on R1 and R2, we will eliminate the need for designated router and backup designated router, and the convergence will be faster. So guys, most of you are viewing my videos and are not subscribed. So if you want to help me and if you like the videos that I am creating, please hit that subscribe button. It will help me a lot. Thank you. Thank you. Now you know more, and if you want to learn even more, you can check my linked Udemy courses in the video description. Also, on each Udemy course, you can find a 30% off coupon, which is listed in bonus section of each course. You will find them listed in the video description. Thank you, and see you in the next video.